Back. This is video 3 of 3 on our lecture on pumps and motors. We're just going to pick up right where we left off here. This is slide 64. We're going to be going through the remaining slides here. So, just to kind of touch on what we were discussing in the last lecture real quick, we talked about flow rates, suction discharge, vibrations, packing, how to do a general inspection of your pump. You want to look at it, you want to touch it, like I said, with the back of your hand, don't touch it with the palm of your hand. And then you want to listen for any kind of abnormalities. As you progress in your water industry careers, if you're out inspecting pumps, you'll learn to identify anything that's abnormal after you've inspected a few of them. So let's get going into the rest of this. So motors, there's a couple different types of motors that are typically used in the industry. Um, Diesel and gas engines, these are not as common. They're usually going to be some kind of a secondary or backup alternative uh, use, only because electricity is the primary use in the industry. Whereas diesel and gas, are for moments when you lose power and you still need those pumping operations. So that's typically what you're going to find out in, a water system. So, like I said, electric motors are going to be the most common type of motor that is used on pumps out in a distribution system, or a pump, or, treatment plant, excuse me. I don't want to exclude that. Um, but the pumps are primarily going to be using an alternating current, power from your power suppliers comes to you in an AC current, and so that's, it's usually a three phase, which we'll get into, and so that's your primary power source for your motors to operate your pumps. Three phase power is what, like I said, like I just said, you're typically going to get that from your power company. Um, it could be stepped down into single phase for lower applications, but then if you got, small motors, large motors, you got to make sure you have adequate power supplies, right? Anytime somebody is designing a system, they should be researching like what, poles are in the area. Do you have, what kind of power do you have coming to you? Because if you're sizing a large motor, but you don't have adequate power supply, you're going to find out real quick that you've got issues. And so that's a lot of stuff that gets factored in or figured out in the design phase. And then lastly, motors are rated in terms of horsepower, which we're going to talk a little bit more about here. So when electricity reaches that motor and it's energized, the motor's going to operate on a principle of magnetism. And that's what's going to create this, like I said, rotating energy. And so what you have here is, like I said, you have a three-phase motor. So you've got A, B, and C phases, and they're all offset by 120 degrees. Together collectively 360 degrees, right? We know it's a full rotation. So then you've got, this electric current that's passing through this electromagnetic stator. And so you have, the different phases are basically chasing the other phase. So A is chasing B, B is chasing C, C is chasing A. And so as those chase each other, they get this they get the motor, or excuse me, the rotor to start to turn inside of the motor. And so it's just this electric current that's constantly chasing the other phases and creating this rotation. Another way of looking at it is that, you could say that the one pole is trying to repel the other pole. So like I said here, opposite poles attract, and so you have, B that's trying to get away from A, and C that's trying to get away from B, and A that's trying to get away from C. But as they chase each other here, you know, rapidly chasing each other with this alternating current, it causes that rotor to spin. And so to measure out any kind of motor imbalance, like if one of the phases is getting more power than another one, there are calculations that you can use. We're not going to use any of these on any of your exams, um, but just to kind of give you the information is that yes, there is ways to calculate this out, and figure out, do you have a motor imbalance? Some of the math that we are going to be looking at in this lecture, refers to as volts, amperes, and ohms, and they make up the mathematical formula for calculating out, your electrical force. Uh, so here we've got volts, right, or otherwise known as EMF, an electromotive force. You might see a question like that. So if you remember this, electromotive force, right? And that's going to be represented as E in the formula. And all it is a measurement of electrical force, which can be equated to pressure. Um, so when you see volts, if you're trying to figure out mathematically, or try to make sense of these things, if you can remember that, uh, you know, electromotive force is the equivalent of pressure, it might help you to rationalize these mathematical problems. Amps are represented as I in the formula, and that is the measurement of the current, the energy that's flowing through that conductor. And so, like if you were to pop that into your equation, it would be, the equivalent of Q, or cubic feet per second. So just to kind of help you make sense of these numbers. So once we get to the formula itself, you kind of understand where all these numbers are coming from. You've got, amps that are, the equivalent of flow, and will be represented as I. And so lastly, we've got ohms, which will be represented as R. And that will be a measurement of resistance. And so we've got now our three letters, E, I, and R. And so together, those will all be put together to create our mathematical formula for calculating various, you know, electrical component or factors of, our motor. And so yes, R is equivalent to friction loss. Okay, so here we are. We've finally reached our formula. E equals I times R. And then you've got P, which stands for power, and that equals I times E, right? So here we go. We got a couple pie charts in front of you here. Again, I like these just because it helps to organize your math, and to work in a direction that will get you to the correct answer. Again, I know some of you like the linear setup, so you can look at those formulas that are up on the top of this image of Ohm's law, and work your problems that way. But for those of you who like the pie charts, again, if you're working your way from the bottom to the top, you're going to multiply, and if you're working your way from the top down, you're going to divide. Let's run through a problem real quick here. You have a circuit that is measured to have 2 amps of current and 60 ohms of resistance. So what is the volts, right? First thing you want to do, grab those letters that we talked about, E equals I times R. So by reading this problem again, we know that we have 60 ohms of resistance. So there's our R. And then you've got your amps, which is the I, and then we should be able to solve for E, or the volts, right? So let's plug those numbers in. You get 120, right? So 2 times 60 equals 120. Okay, so here we're going to work in the opposite direction, right? So in the last equation we multiplied. In this equation we're going to be dividing, right? So the problem reads, how many amps of current are present when a circuit has 480 volts of electromotive force and 60 ohms of resistance. So in this case, we're trying to solve for I. And so our equation will be set up as such. I equals E divided by R. And so if we take the information that we have from the problem, plug it into our equation, you've got 480 divided by 60, and that will net you 8 amps. Again, if you're looking at this, E divided by R will equal I. So another factor to take into consideration is that there are three classes of three-phase motors. And there's the squirrel cage, the synchronous, wound rotor induction motors. And depending on what it is you're trying to pump, what you're trying to accomplish, that motor design will need to match the application. And so, like I've got listed here, there's many different, applications that you may be trying to achieve. And so it just, depending on what it is you're trying to do, will dictate what type or what class of motor that you're going to need. First, let's talk about the squirrel cage induction motor, right? So this is going to be the most common type that is used in our industry. And as you could tell by the design of this cage, it looks like a squirrel cage. And the rotors are, the rotor bars are not parallel to the shaft, right? They give it that, skew, so that way, when the phases are applied to it, it will create this, repel or attraction, or whatever, a way to chase or repel the other phases from one another. And so that's why it's given that skew. Here we have the synchronous motor. Um, Typically, these are going to be used in like an industrial type setting, for large blowers or crushers, like some kind of power factor, uh, you know, or power plants, excuse me, is where you're going to find like a synchronous motor. And the key feature that makes it a synchronous motor valuable is its ability to maintain a constant speed under varying loads, which is ideal for like precision driven and high performance applications. And so the way they work is that you've got this AC motor that rotates at a speed that exactly is synchronized with the frequency of the AC supply current. Its operation is based on this interaction between a rotating magnetic field generated by the stator and a magnetic field generated by the rotor. So here we have the wound rotor induction motor. And it's a type of induction motor where the rotor windings are made of insulated wire. And then they're connected to an external resistance through slip rings, which we'll talk about soon. And this allows for a better control of the motor's performance, and it allows for more of a controlled acceleration or better starting torque than the other motors, and these can be adjusted. So unlike the squirrel cage rotor, which has this fixed conductivity, the wound rotor is connected to external resistances via these slip rings and brushes. And so these slip rings are these metallic circular rings that, are mounted and rotating with the rotor shaft. Whereas the brushes are these spring-loaded are spring-loaded to make good contact with these slip rings and are connected to the outside circuitry and do not rotate, so they're fixed in place. And so these motors have, of course, their advantages and disadvantages. Um, you could say that, the advantage is that they have a better starting characteristic than the squirrel cage motor. However, they're less efficient due to the slip ring and brushes or the rotor resistant losses. But then, on the one hand, you've got greater control over the torque and speed, over the other motors. But there's more maintenance involved due to these slip rings and brushes. And they're more expensive than the other more induction motors. So it just depends on what it is you're trying to accomplish ultimately, and how these pumps, are needed in the system. It depends on what you're going to use. So when you have motors, obviously, they cost a lot of money. So you want to ensure that there are ways to protect that investment. And so these motors will come equipped or built in with these motor protection systems, right? Some will be the thermal overload relays, right? So as temperature reaches a certain point, eventually it will cut that motor out to prevent frying, or burning up anything. And then you have fuses or circuit breakers, just like at your house or your apartment, whatever. You've got fuses that are, only rated to a certain amperage and will pop once they reach that point to prevent damaging any of your equipment. And then you got overcurrent relays, right? So, if they're detecting a high level of current, but then you can have an undercurrent relay as well. And so to explain current, I've got the graphic here, and you can see that, you've got with a large current, there is many charges, right? This is like on a molecular level, that you've got many charges flowing in one direction, whereas a small current, you're going to have fewer. So you've got that thermal overload relay that will measure the temperature of the motor and then provide that feedback. So once it reaches a certain temperature, it will, like I said, it will cut out. These are typically the most popular because they are so inexpensive and they're widely available. It doesn't require a whole lot of parts for these to operate. And so a lot of times you're going to find that your motor has some kind of a thermocouple to prevent any damage to the motor or protect the motor, if you will. Okay, so here I've got a nice general, drawing of what a thermocouple is, right? You've got a voltmeter, and then you've got two dissimilar wires, right? One will typically be made of iron, and then the other will be typically made of copper. And at the location where the two wires meet, that is known as a hot junction. And the two sides, or the other side of this, where the wires are separated, that's known as a cold junction. So when the hot junction is exposed to heat, that temperature gradient is created, and the hot junction and the other end of the couple will, you know, create this difference in the electron energy level of the two metals, and which generates a small voltage. So that small voltage is then generated on the cold end. And so that's how this thermocouple is reading the temperature. So once it reaches a certain point, though, it's designed to cut out and protect your motor. So these things are pretty simple. And like I said, they can actually be used for a wide temperature range, and they're ideal for, industrial and scientific applications, right? Just based on their simplicity. So this is essentially how a thermocouple works. Another type of thermal cutout switch or thermal overload relay would be a thermistor. And so these are typically constructed of like a cobalt oxide, which is a conductive material or semiconductive. But then it has this inverse relationship. So as temperature increases, the resistance will decrease. And then that'll send a signal to a circuit to trip when it reaches that set point. The nice thing about these is that, they're much more accurate than the thermocouple. Um, but they use a larger output signal, and they have a more narrow range. Um, but the nice thing about them also is that, the calibration is maintained for much longer. So you don't need to calibrate this type of device as often as you would like the thermocouple. So another thing to take into consideration, obviously, is this inrush load, or current, right? So as current is applied to the motor, a lot of times you have to apply 5 to 10 times the normal operating current in order to get it started, right? You need to have this high torque in order to take it from a rest into full speed, right? And so the time for it to go from, full rest to fully operating at its normal operating set point, it could be between 1 and 8 seconds. And so that starting current is also referred to as inrush current, locked rotor current, and motor starting current. And it's really important that you take these things into consideration, because you can actually damage your motor by not applying enough current or applying way too much current. um, and so, managing this locked rotor current is essential for protecting the motors, minimizing voltage drops, and ensuring a smooth motor operation. So, some of the things you might want to keep in mind with this slide is, I might ask you guys, how many times the normal full load current is the inrush load on a motor. I know I saw that on my distribution exams, so I'm going to ask you on your exams as well. So how do you control all your motor? Well, you have like a motor control panel, right? And inside that panel, you're going to have fuses, sensors, your contactors, processors, some kind of a thermometer, and it's going to be fully enclosed in this enclosure. And so it'll have the HOA switch. Uh, it's all contained in this one spot for each motor, right? So each motor should have its own motor control panel. And so here in this diagram, you can see that, there's a lot of different components inside of it, and that's just kind of a typical motor control panel and some of the components that you're going to find inside of there. In a typical pump station layout, most pump stations, there's going to be a lot of a lot of pumps, a lot of motors, a lot of motor control panels or PLCs. You're going to have, a lot of stuff inside these pump stations. But the ultimate goal is to be able to meet the demands of the system, depending on the season, right? So you want to be able to, you know, provide water at its maximum, but then also have your pumps be able to provide water at a minimum. And then, you should always be able to provide that even when one of these units is out of service, right? So it's always important to have some kind of redundancy in there. Maybe it's, you take down one pump, but you have another pump station that can back up, the pump, your main pump station, or, secondary pump station. And so, reliability and redundancy are just as important as the layout of your pump station. So in this image, I got a nice indoor pump station here, lots of working room to get in and around these pumps. On the top of the pump, you've got your motors here. There's four of them, and then you've got this little sight glass that you see up near the top, and and that's the oil level, or sensor, not sensor, but an oil level sight glass, so that we could see, do you have proper amount of oil in there? You're not too high, not too low. And then you've got this screen just below the motor, at the coupling between the pump and the motor shaft. And so obviously it's got a screen on there. You want to make sure that that is protected. If you stick your hand in there in operation, it can lead to serious harm and injury. The pump itself here, it's got that radial flow like we've discussed in the other videos where it comes up, it makes that 90-degree turn and then is sent out into the distribution system. This is a bit taller coupling, when you need to detach one from the other, these make it much easier to pull these things apart. And then here's that auxiliary valve. So these valves right here are going to be closed, and as the pump is started against this closed valve, it'll slowly push this open, and then discharge that water out into the system without causing any kind of water hammer. Um, it looks like down here in the back of this image, you've got another regulator. A lot of times, if your pump is running and it doesn't cut out once it reaches a certain pressure point, this will open up and either discharge, into like a lake or, it's just somewhere, or it'll discharge back into the low pressure side and keep recirculating to prevent, overpressurization. But otherwise, this is a really nice facility. In this image here, you can see this is an outdoor pump station, connected, right downstream of your reservoir. So in this scenario here, you have a suction head scenario, right? So it's not a suction lift, a suction head. You've got your source water that sits above your pumps. And then, yeah, again, pumps are, there's probably a large water main that sits below these and it draws off of that and, pumps it out into the system. If I had to guess, I'd say that it looks like they got a VFD in here to provide that variable frequency, depending on the pressures or the demands downstream. You want to be able to just meet those lower ends, whereas you got some heavy hitters here that will relocate this water into maybe another reservoir or pump out into the system, in times of high demand. And then here's a design of a pump station that you would see on a set of plans. This will, this looks like it, it's probably their as-built. They've got some specific dimensions on here. So this is probably an as-built sheet. But yeah, it's just a real general pump station, right? You got water that is coming into the pump station from this 24-inch CMLC pipe going through your pumps and then being discharged out into a 16-inch concrete line pipe. And then, like I said, here's that recirc, so if it overpressurizes, this valve here will open up and then discharge back into the low suction side to prevent, overpressurization. And so, yeah, this is just a, basic as built of a pump station. So with that, that concludes our lecture on pumps and motors. If you haven't already taken the pumps and motor course, I highly recommend it. You probably get a lot more information out of it. I'm just trying to, provide you guys with some real basic general information about pumps and motors, in case you're not taking the pumps and motors class. So that way, if you're asked questions on your distribution exam, you should have no, you should be able to have somewhat of an idea of how to answer those kinds of questions. If you got any questions, though, please don't hesitate to reach out and let me know. Otherwise, have a good week.